Okay, let's talk about the single most violent, most transformative event in the history of, well, everything. It's called cosmic inflation. And this wasn't just some big explosion. No, this was an insane period of hyper-acceleration that took a speck smaller than an atom and laid out the entire blueprint for the universe we see today. And when did this happen? It happened fast. I mean, unimaginably fast. This number you see here, that's the moment inflation kicked into gear. A trillionth of a trillionth of a trillionth of a second after the Big Bang. I mean, that's a decimal point with 35 zeros before you get to the 1. It's just wild. And the scale of this expansion is almost impossible to wrap your head around. In less time than it takes for light to even cross a single proton, a patch of space smaller than that proton ballooned out to become larger than a galaxy. That's right, space-time itself was expanding faster than the speed of light. Now, you might think this all sounds like science fiction, but you see, inflation isn't just some cool idea somebody dreamed up. It was actually born out of pure necessity. By the 1970s, the standard Big Bang theory had some huge, glaring problems that were keeping cosmologists up at night. So, puzzle number 1, the horizon problem. Here's the deal. When we look out at the oldest light in the universe, the afterglow of the Big Bang, it's shockingly uniform. It's the same temperature everywhere we look, to an incredible degree. But how is that possible? In the standard Big Bang model, opposite sides of the sky have never, ever been in contact. They shouldn't have had time to talk to each other and even out their temperatures. There's a great analogy for this. It's like walking into a massive mansion and discovering that every single room, from the attic down to the wine cellar, is at the exact same temperature. But you know for a fact the heating and air conditioning have never been turned on. It just makes no sense. Something is missing from the story. Okay, on to puzzle number 2, the flatness problem. It turns out the geometry of our universe is, well, flat, and it had to be exquisitely fine-tuned right from the beginning to end up this way. If it had even a tiny bit more curvature, it would have collapsed back in on itself billions of years ago. A tiny bit less, and it would have flown apart so fast that no galaxies could ever form. The precision required is just staggering. It's like trying to balance a pencil perfectly on its tip and having it stay there, perfectly balanced for 13.8 billion years. The odds of that happening by chance are basically zero. And finally, the third big headache was the monopole problem. Our best theories of particle physics, the ones that try to unite all the forces of nature, they all predicted that the super hot, super dense early universe should have created a flood of these weird, heavy particles called magnetic monopoles. They should be everywhere. But the thing is, we've looked, and we've never, ever found a single one. It's like a cosmic missing persons case. So there you have it. 3 huge, seemingly unrelated cosmic puzzles. And then, in 1980, a physicist named Alan Guth came along with one single, beautiful, elegant idea that solved all 3 of them in one fell swoop. He called it cosmic inflation. The idea is that for a brief moment, the universe was filled with this bizarre energy field, the inflaton field, that basically had anti-gravity. It pushed everything apart, forcing space-time to expand at a truly exponential rate. So how does this one move solve all 3 problems? Let's check it off. The horizon problem? Gone. Our entire observable universe grew from one tiny microscopic patch that was connected and had the same temperature before it was blown up. The flatness problem? Solved. Inflation stretches space-time so much that any initial wrinkles or curves get smoothed out, just like blowing up a balloon makes its surface look flat. And the monopole problem? Gone. Any monopoles that might have existed got spread so far apart that the chance of finding one in our observable universe is practically zero. Clean sweep. But here's where it gets really amazing. Inflation did way more than just fix old problems. Its greatest triumph, its biggest legacy, is that it actually explains where everything, every galaxy, every star, every planet, came from in the first place. See, down at the quantum scale, nothing is ever perfectly smooth or still. There are always these tiny, random fluctuations in energy, these little quantum jitters that are constantly popping in and out of existence. The inflaton field was no different. And this is the magic trick. Inflation took those microscopic, subatomic quantum jitters and stretched them, blew them up to astronomical scales. Those tiny little energy fluctuations became the slightly denser and slightly less dense spots in the early universe. They became the gravitational seeds around which all the matter would later clump together to form the vast cosmic web of galaxies we see today. Now that's a beautiful story, but great stories aren't enough in science. What makes inflation a truly powerful theory is that it made very specific, very testable predictions. And decades later, we built the technology to actually go out and look for that evidence. And these weren't vague predictions. Inflation predicted the universe had to be flat. It predicted the exact kind of pattern those density variations should have. It said they should look pretty much the same on all size scales. And maybe most importantly, it said they should have a random, bell curve-like distribution, a very specific statistical fingerprint. So we launched a series of incredible satellites, COBE, WMAP, and then Planck, to map that ancient light, the cosmic microwave's background, in stunning detail. They were looking for that exact fingerprint left behind by inflation. And the results were absolutely staggering. First, they confirmed the universe is flat to within a 0.4% margin of error. I mean, that's 99.6% of the way to being perfectly flat, exactly what inflation demanded. But it wasn't just the flatness. The pattern of those hot and cold spots in the CMB, their sizes, their distribution, it was a near-perfect match for what inflation had predicted all those years ago. It was one of the greatest triumphs in the history of cosmology, a total home run. So, inflation is on incredibly solid ground today. But the theory itself, when you follow its logic to the end, leads us into some even more profound and mind-bending territory. One of the weirdest implications is that inflation might not be over. The idea is that it might stop in some patches of space, like ours did 13.8 billion years ago, but continue raging on forever in other regions, constantly spawning new space. They call it eternal inflation. And that leads to this final, incredible question. If inflation is constantly creating new patches of space where it stops, could our entire universe just be one bubble in a vast, frothing cosmic ocean of other bubble universes? A multiverse? That's the frontier inflation has opened up for us, turning the blueprint of our own cosmos into a possible map to countless others.